All right. Hello, everyone. Let's switch to English, mostly because so that I don't have to hurt your ears by translating strange words related to multithreading. Well, let's start with a few words about me. I'm doing Java professionally for over 15 years, other programming languages a little bit more. Well, I started as a basic programmer on Commodore 64, if anyone recognizes this beautiful machine. Currently, I'm a trainer in EPAM, and I'm working with junior developers, trying to pass my knowledge about various topics related to computer science and information technologies to prepare juniors for the project so that they can jump straight into the project and deal with the tasks efficiently. Here are some, there's some information about my, contact from me. So if you would like to reach out to me, don't hesitate. And this topic, the topic I'm going to talk about is multithreading. But multithreading in a slightly different way than usual, because, well, if we think about multithreading, in theory, everything should actually work fine. But when it comes to practice, well, not exactly. Often there is a, well, it's far from expectations. We get some kind of freezes, or something blows up, or the data is changed in an uncontrolled way. So working with multithreading is difficult. And I used to have the same problem with multithreading until I found a nice way to work it out, to think about multithreading. And in EPAM, while I work with those juniors, I was looking for a solution for how to pass the knowledge, especially about such difficult topic, to people who don't have really coding experience that much, like a senior developer, right? So not 5 years, not 10 years, but just, let's say, from 1 year, they just start working with Java. And then there is such topic like multithreading. So, well, let's see how it actually looks like in, well, without, when normally junior people try to start their adventure with multithreading. So let's start with some definitions. As you can see, those definitions are taken from Wikipedia. Usually the first choice as a source for knowledge for junior developers. And these are the very first sentences from those articles. And they use often very complicated terms which are hard to understand for those people. So when they look at it and they start doing multithreading and they read about it, they, well, might look like something like that. The head blows up, and what actually is this about? And often when I worked with my trainees, this was the situation. They had they were really confused about such complex terms like those, because multithreading adds an extra level of complexity to a program. So if your program doesn't work sequentially, it's not gonna. Well, multithreading is not gonna be a solution for that, definitely. So I started looking at the ways how to explain that easily and in a pleasant way, hopefully. So after several attempts of well, searching for such solution, I actually decided to make it a game. So I devised a game to work with multithreading, to explain people how those concepts can work, but in a slightly different way than usual. That means around 2 weeks before actually mentioning during the training about multithreading, I started giving those guys some time. Hey guys, here, just chill out and have some well, fun and pleasant time with a simple game, without mentioning a word that it's related actually to the topic that we're going to cover in 2 weeks. So this is a board game which I devised, and let's go through the rules of the game. I'm going to describe you some specific mechanics of the game so that you can get the feeling of what's going on there. So the basic elements of the game are portals. The game, the goal of the game is to travel through portals. Think about that for example, for fans of maybe Stargate movie, you can imagine that portals are actually those gates which you use to travel, move the pawns from one side to another, one side of the portal to another. And we have pawns, we have places or platforms which we use simply to put the tokens or pawns on them before they go through a portal or after they exit the portal. The rules are very simple. The goal is to bring a pawn for each player, bring a pawn to the center of the board, and then get rid of the rest of your pawns. This can be achieved by simply building a road. So those guys, each player needs to get to the center using the road he or she built, probably often with support or from other players. Other movements include introducing a pawn to a board or moving the pawns to through portals, and then of course every action is mandatory. If you can make a move, you need to make it, and there is some randomness included because there is a dice roll which decides which kind of action is going to be performed by a given user in the given turn. So how does it look like in details? A portal is a passage between input platforms and output platforms. We can have one-to-one, for example, one input platform and one output platform for a given portal, but there can be more of both. So you can have more. You can have one input or and two outputs, or two or three inputs and one output even. And as we can see, as we will see later, it's even more interesting at some point. So launching the portal, so making a move which moves the pawns, works like that. We simply take all the pawns from the input platforms and we move them to the output platforms. The thing is that we do that all at once. So a portal, for a condition for a portal to be active, is that all inputs are occupied and the outputs are empty. And after the move, it's the other way around. All inputs are empty and the outputs are all filled with tokens. So right. So the portal needs to be active before it can be launched. So a situation where there is another condition here, in which all the pawns on the input platforms need to belong to the same player. And as you can see on this image here, we have a situation which makes it not possible to activate the platform, even though all inputs are occupied, because there are pawns of different players on the field, right? Other situations, like not one output field occupied, or not everything is filled. These are kind of basic rules for the game. There are a little bit more than that, but another specific thing about the mechanics of the game is that when a given field or given platform is connected to more than one portal and it's active, both are active, we can simply choose, the player can choose which path to go. And after making a move, the second platform simply becomes inactive. So only one move is possible during each turn. And the interesting thing that I mentioned previously is that we actually can, after walking through the portal, we actually can have more elements than we had, more tokens on the board. So we introduce more tokens to the board, or we can actually reduce the number of tokens on our tokens on the board. This is something that is necessary to accomplish the second goal of the game, like remove all other tokens, our tokens from the board. So now, this is actually all about the mechanics, and you might wonder why I am actually going through all those rules, which you probably won't even remember. But bear with me, please, and we're gonna reveal the mystery. So with that, we started playing. The initial version of the game was actually something like a board game, more precisely a whiteboard game. So we did this kind of setup with the projector, and we simply drew all those platforms and portals on the whiteboard. As a team of, let's say, 12 people, divided by into 3 teams, we had a lot of fun with that. And there were various situations in which some of users, there were some alliances forming, and there were some users, some malicious users, malicious players who tended to block other people from making actions, and so on and so forth. So a lot of fun during the game, which simply people didn't actually realize that it's gonna teach them something. So we played even more, just to make people familiar with the mechanics of the game. And then the day came. After 2 weeks from the initial introduction of the game, we started talking about multithreading. So unraveling the mystery. And after this example, after the game, I showed the people this simple example of something that is usually very often used in terms of when we talk about presentation, when we talk about multithreading and issues related to multithreading. As some of you probably already know, this is a simple incrementation like X++ operation in Java. We all know that this operation is not atomic. So it needs to be, in order to ensure that it's going to be executed properly, we need to ensure that that the entire operation is performed atomically by a single thread without any interruptions. So this I showed this diagram to people, and they say, "Oh, there's portals. Awesome. So then a simple translation of terms appearing in the game to the concepts of multithreading. And then there's illumination. People start thinking about multithreading, referring just to the concepts that they acquired during playing the game. So people suddenly realize how those threads are actually working. Of course, we also need time for that time to simply get used and practice with that to well, get used to the analogy and start thinking in a visual form like this about multithreading. So let's go through a simple example. If we have a counter, which is, of course, not exactly thread safe, we know people think that well, at the beginning, people might think that, oh, it's a single operation, so it's definitely going to be a thread safe, right? But when you split that into separate instructions of the bytecode in Java, we can see that it's not exactly that thread safe as we thought. Because if thread 1 appears and loads the value of the X field, and then another thread comes while the first thread actually is actually performing the operation and working on the already loaded value, the same thread well, the other threads can simply perform in parallel. But we know that right now, if those two threads are going to conclude their actions, so try to store the value, well, just if we start with simply a 0 value of the field, then we have actually an incrementation with a loss of value. So value of this, we have a dirty write, so write operation. So one of the threads, the result of one of the threads is going to be simply overwritten. So how can we fix this issue? And now the solution for this race condition, so-called, is simply synchronization, or trying to put a lock on the operation. So making sure that this operation is going to be atomic. So how does it work? Well, a thread comes in and enters a critical section. Critical section here is marked by an additional platform, or in the middle, which forces another thread to simply wait. Because as we remember, when we activate this portal here, well, if this portal has two outgoing platforms, so this platform is occupied, that means that this player simply cannot enter this portal because, well, there's no room to exit, right? So this leaves the first player, the opportunity to perform action without any interference. So the player 1 ends the procedure and commits the changes, and then simply another player can enter and perform the operation and commit the changes as well. And in this situation, there is no loss of information. So later on, when we have the idea of race condition, the first the danger or first risk that we can encounter when working with multithreading, it's time to define the rest of very common concepts that are necessary for juniors to acquire. One of them is a deadlock, a situation when, of course, as we've seen in the definition from Wikipedia, several threads are waiting for two resources to acquire two resources, but they cannot because they only can acquire one, right? So if they acquire just one of those two resources, they simply cannot proceed because all other threads did exactly the same. And we have a deadlock. A similar situation, well, the solution, potential solution that we can think of is simply allowing those threads to resign, to unlock the resources and let other threads work, well, perform their work, and then we're gonna resume. So let's try. But this situation actually causes another potential problem with multithreading, which is called Livelock. So if all of those threads simply resign at the same time, like this, then, well, all of them have the possibility to move on to the next platform, but they lose the lock on the previous platform. So we have the following situation: just simply rotated, the state becomes rotated, and we actually didn't change anything. So if we the repeated situation like this can simply cause just increased CPU usage, and none of those threads will be able to perform the job. Now, once we have those concepts of livelock, of deadlock, of race condition, and possibly other situations, other problematic situations explained, well, the time has come to reveal the full set of information, the basis for all of that. So we had this walkthrough through the rules of the game, just so that you can realize that those rules, actually those participants of the training, well, and kind of unconsciously learned an interesting framework that I would like to talk about further. A framework that allows us to visualize and work with multithreading in a scientific way. And this diagram here that we can see, which is, of course, the game is actually modeled after, is called Petri Net. And it was devised by Carl Adam Petri, well, quite a long time ago. And this currently serves as a model for various concurrent and distributed systems. But multithreading is just one of those applications of this formalism. So as you know, when we talk about well, object-oriented programming, for example, we have UML which we can use to discuss to transfer our thoughts or our reasoning to other people. We can go to the whiteboard and we can draw various class diagrams, object diagrams, sequence diagrams, maybe. And this is a common language for talking about object-oriented programming. In case of databases, of course, we also have such diagrams. However, diagrams for multithreading are not exactly that known, at least not that well known, right? So there are things like BPMN for describing processes, but they're complicated. They have a lot of boxes, a lot of arrows, and semantics is actually quite sophisticated. We have activity diagrams in UMLs. We have flowcharts, which we can also try to use to describe such concurrent systems. But they all simply rather focus on the flow of the data, and we forget about, actually we lose the focus on the potential issues that can appear. Petri nets are a great, very simple way of visualizing those exact problems. So if you take a look at the terms, those platforms are actually called places in Petri nets. Portals translate to transitions. Arrows are arcs, which connect places and transitions with each other. And then we have tokens, which well, appear on places and move from one place to another through the transitions. A very simple framework, very simple set of operations, set of constituents, gives us quite low level, entry level, to simply describe the processes, the concurrent processes, and to be able to simply see things like deadlocks, things like well, concurrent modifications of some shared resources. So the benefits that we get from Petri nets as a modeling language for distributed systems is the simplicity, just 4 basic building blocks. And apart from that, well, despite the fact that this language is that simple, it has a lot of expressive power. It serves in many situations as the way to define the semantics even for flowcharts, UML diagrams like activity diagrams or BPMN, or many other. If you take a look at the Wikipedia, you will find many other applications for that that kind of systems. So this is actually this becomes a great tool when working with dependencies on in many domains, not only computer science like this, but also biology, chemistry, and many other and in industry like well, any other industries. Another real benefit, which is not exactly that clear in case of BPMN or activity diagrams, is, and which comes from the simplicity of those diagrams, just 4 elements, just 2 kinds of vertices in the graph connected with some edges. This gives us a very big analyzability. This modeling language is a mathematical language, so it is backed by a heavy maths, which, as you know, in case of anything related to mathematics, it's strict. So there is no room for interpretation or over-interpretation. And if something is clearly mathematically defined, we can actually draw some conclusions about that. So, for example, we can analyze our Petri net, which is drawn by us, well, based on our concurrent system or the idea of our concurrent system, and we can prove, actually, in many cases, that our network is going to be free from deadlocks or other unwanted situations. There are many properties of Petri nets, such as, well, reachability or liveness, which can be mathematically checked, and this check, in most of the cases, can even be done automatically. So this becomes a great tool for checking if our programs are really thread safe. Now, I suppose you already know when you were working with multithreading, that testing multithreading is not that easy, right? It's probably, as far as I remember, there was a a survey some time ago about how many people in the world, how many developers do test multi-threading. And it turned out that it's actually at the level of 6% or something of people who actually do any testing of multi-threading. That's very surprising, considering that the complexity of which is introduced by multi-threading is much higher than the sequential application. So if you decide not to test a much more complex solution, you're just simply asking for trouble. Petri nets are a formalism which allow you to build, to test your solution, the model of your solution, against things like deadlocks, like maybe starvations and other unwanted events. And finally, there are tools available for working with Petri nets in the net. So you can search using your favorite search engine for tools. In most cases they are free. They are even open source, and they are multi-platform. So, for example, written in Java. Those tools allow you to edit such diagrams. Of course, editing diagrams is nothing difficult. We can do that in a simple graph editor like our diagram editor. But those tools allow you to, once you prepare such a diagram, they allow you to perform a simulation. They can generate the tokens for you and put a heavy load on your network so that you can see easily where your network simply blocks or where you get stuck in the process. That's very useful, especially when we work with highly concurrent systems and with many threads and many items of data going through the application. So with that, we can simply see where are the bottlenecks of our application. And of course, this basic version of Petri nets that I encoded in the game they have some level of expressiveness, but sometimes it's simply not enough. So some people devised other frameworks, extensions of Petri nets, but by adding additional features. Of course, that made them a bit more complicated, and some problems turned out to be not exactly decidable because of those extensions. But the expressiveness of those extensions gives us even more opportunities to analyze our systems, to express the conditions of our application, our concurrent systems. The generalized Petri nets, for example, allow us to put more than one token on the place, while the classic Petri nets allow only single token on a given place. Then we have colored Petri nets, another very popular extension, which on the other hand allows us to distinguish between the tokens. Normally, the tokens are simply considered identical, so you can't distinguish between two tokens from different places for the transition. Colored Petri nets introduce something like values for tokens, which are called colors, and they allow you to define some conditions for transitions, which decide whether the transition fires or not, according to the tokens that are in the input places. And also, there are some expressions which allow us to translate those values or perform some mapping of those values to to the output places to simply simulate the computation. Yet another framework allows us to introduce time factor in the application. So in our Petri net, we're gonna be able to introduce some delays, for example. This might be very useful if some of the transitions needs more time simply to perform the operation to fire. And then there are also prioritized Petri nets, which simply allow us to give some more importance to some transitions and less to the others, so more priorities. Now, once we do that, once we know that what we are dealing with, like Petri nets and other extensions of those, we can simply practice that by trying to model a very simple yet challenging concurrent system that we actually are all familiar with, or most of us, those which have driving license, for example. And this is another task that I give to the people so that they can practice working with concurrency on example of a circular junction or roundabout in two forms. One which in Poland is actually more common, the one which gives the priority to the vehicles which are circling around the junction, and another example as for where the vehicles which are entering the junction have the priority. So the right-hand rule works here, and this gives us a lot of fun as well, because there's it's really challenging to figure it out, and once we figure it out correctly, it gives us a lot of satisfaction when we solve the problem. And then another exercise which allow us to check our full understanding of the concurrency by simply learning synchronizers in Java. So we have a bunch of synchronizers since Java 7 or Java 8 even. Some of them are also in Java 5. But in order to understand how they work under the hood, well, we need to read the documentation and things like that. And still, to fully understand, it's actually quite difficult, especially if you take a look at the sources. But using a visualization like the Petri nets, you can give yourself a better understanding of how the system behaves inside, and how those synchronizers can affect the complexity of your application, and how you can build your application using those patterns, those concurrent patterns like this, to build more complex systems. So just to conclude, after all those additions, when I introduced the game to the people, I collected some observations. One of them is that learning through play really helps people to assimilate or to get used to how the concurrency work, and the visual representation really helps them to understand the flow of the concurrent application. Again, another interesting thing is that the situation they encounter during playing the game, unaware of the multi-threading aspect of that, those situations stay in their heads and allow them to simply recognize those patterns and recognize those bad situations, to identify where where such multi-threading can simply break your application. And the last thing is that the thing about the definitions, postponing introduction of those difficult terms, but replacing that with a piece of entertainment gives really, reduces the level of stress and allows to more seamlessly assimilate the knowledge and get used to learn the things in a more efficient way. After that, what actually made me think about presenting the topic to you here is the impressions, the feedback that I got from the people who actually played the game, and from that feedback, I learned that the game allowed those people to learn seamlessly, to visualize how the network, the concurrent processes are working under the hood, and this all in the fun way, leaves makes it better remembered by those people. The references are quite well known, the Wikipedia here. So this is a starting point for many people starting their adventure with multi-threading. So we can take a look at that and try to read more about it. Of course, Petri nets in Wikipedia are not that easily explained. There's a lot of maths there, so it might be a little bit difficult for a junior developer to take a look at that at first. But if you remember all those rules and try to simply think about the way the tokens move through the diagrams, it gets much. It's actually enough for many situations, and the formalism comes later when you get familiar with the mathematical notation. And it's, of course, not exactly obligatory. So with that, I would like to thank you very much. And I'm hereby giving the voice back to the studio.